So now finally, we've talked about some of the basic ways to solve first order differential equations, right? The only time that any higher order has come up has been something simple like just verify this is a solution. So you just have to be able to take derivatives. So chapter 4, we're finally going to get into how do I solve higher order derivatives. So, you know, they're going to have a few problems where it's going to be some verify stuff again, but we're just going to jump into something more interesting. I think I've talked about this before. So higher order diffie Q. I'm not going to write the whole damn thing out. Yeah. Blah, blah, blah. All right. I'm going to do this a little out of order from what the book does. Here is a word that's going to come back that is going to haunt us a little bit, right? And I think back in chapter 1, we actually introduced this word, and now we're used to this word meaning something else. In the context of a higher order DE, homogeneous means it equals 0. So is this homogeneous? Well, it depends on what that is, right? So if this is not 0, this is non-homogeneous. If this equals 0, it would be homogeneous. We call it homod. All right, so that word is a little bit evil. So it means sort of, it's a method that we use substitution-wise, but normally it means a diffie Q that equals 0. I like it. And we've talked about initial value problems. And I'm pretty sure I talked a little bit about boundary value problems, but let me just go over those again. How many initial values should I probably get for this, do you think? So if I have a first order, I need how many? I need 1, because I'm going to get possibly 1 constant. So here I could need up to n initial conditions. How does this book show them? Y of x naught equals y naught, y prime of x naught equals y1, blah, 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 blah. Notice, initial value problems mean that all of these depend on the same input. They all come from the same x value. Boundary value problems, I love the idea of boundary value problems because and when I normally think about this, I think about quantum mechanics, which is where you have like an electron trapped in a well or something. That sounds like, you know, Lassie comes in, there's an electron in a well. But you have something, you have only certain wave functions that could fit in here, and that's the boundary conditions have to be met. So that's why the way I remember boundary value is they don't relate to the same x. They relate to 2 different values of x. X equal a, x equal b, whatever. Does that difference make sense? And in solving these things, you don't have to remember which one is which. You do the same process to solve it. You use what they tell you to figure out what the constants are, as always. So this would be y of a equals y1, y of b equals y2, and then however many more they need to give you. I like it.
Is this like in Calc 3 when we had boundaries like
Oh, you had to determine, you had to check the stuff on the boundary. No, not quite. That was more to determine the max and min on the boundaries of some, right? Is that what you're thinking about?
Yeah.
So that's not really this. This is forcing the answer to have a certain value at these boundary positions. So that's a little bit different. So that's not quite like checking the boundary of some region for something yet. I like it. I like it. I already talked about that. I like it. I like it. Oh, just to give you a little bit of motivation for what's going to happen. Let me leave this up here. You guys have this. This is old news. We've done this already a few times. I don't think we've had a problem like this one yet, but it works a lot like this does. me just throw this up here. This is something I think I've said before. And you see this every now and again, especially with sine and cosine. You see these problems where they say C1 sine of something plus C2 cosine of something. And it's because sine and cosine both have the same relationships with their derivatives. Does that make sense? So if I said, can you determine on site what the solution to this is? So the second derivative of something plus the original thing is 0. What would that be? What's the second derivative of sine? Well, its first derivative is cosine, and then another derivative is negative sine. So sine and cosine are both the opposite signs, SiGN, of their second derivatives. So they both solve this. So the actual general solution is would be, so this is what this is saying. Y1 equals sine solves this. Y2 equals cosine solves this. Therefore, y equal to C1 sine x plus C2 cosine x solves this. We've seen that before, but I just want to throw that up there to make the bridge. We've seen it before. Now let me show you a different way to write derivatives using something called operators. And operators are going to become very useful very soon. So we've seen this kind of thing before. That's all that's saying. And really, it's because of the fact that derivatives have this linearity. They're linear operators. So let me first show you what the hell an operator looks like. So just to start off with the basics, dy dx, I can call that dy. I like it. And you're like, wow, that's amazing. Right, but trust me, you gotta believe me, this is gonna become very useful. So like if I had d cubed y dx cubed, that would be d cubed y. Amazing. So the nice thing is, what do you think this would do then? D plus 3y. What does this operator want to do to this function? It wants to take derivative, right? First order derivative. And it wants to add 3 times it. So it would become dy dx plus 3y. That's what that would represent. On one level, it's kind of like, okay. But it's going to make things look a lot easier. It's going to make our job easier later. But this makes it a lot easier to see and to remember that derivatives are linear. So if I had, how would I write d squared y dx squared plus 5 dy dx minus 7 y equals 0? I would write that as d squared
plus 5.
And see how this, now that really focuses our attention, that looks a lot like a polynomial. And there are methods that treat these things as polynomials. It's kind of nifty. So if you've taken, again, I know I keep saying this, but if you've taken linear, you've seen the idea of operators. You know what operators are. When you apply a matrix to something, it's actually applying an operation to that thing. It's transformation, right? So derivatives are linear operators, which is why this kind of thing works. This superposition is what it's called, the superposition of answers. Okay, I like it. Let me just let all that sink in. Yes?
How would something be like squared and be linear? There's one derivative for all.
But again, that square isn't really a square. It just means the derivative is being applied twice. So it's really, The reason that we do a square is because how would I really do this? Well, that means d by dx of d by dx of dy dx. So that would be dy, a d applied to that, and a d applied to that. So it really is just a symbol convention. It doesn't mean that d is multiplied 3 times. It just means let me collect this and say I apply the derivative operator, in this case 3 times, in this case twice. I like it. So it's sort of the idea of order and degree really being put in your face now, right? So the degree of the linear derivative polynomial that I could make is equal to the order of the differential equation. Ooh. All right, I love it. Some of you guys are gripping your desk. Yes?
How does that operation relate to the superposition?
So just the idea, if I write it as an operator, and I start working with it. Now, of course, I'm not going to go back and show you derivative rules. We all know derivative rules. You should know that derivatives, if I take the derivative of a polynomial, I can take the derivative of each piece. That's the idea of a linear operator, that it looks like it distributes. That's what it means to be a linear operator. This is all about the fact that if I took the derivative of just that piece, it works. So if I take the derivative of just that piece, if I put that into the equation, it works. So of course both work also because the derivative is linear. I can actually break this up into derivatives of this plus derivatives of this. They each separately equal 0, so of course together they equal 0. So if I really want to look at this, what does this look like in terms of big old d?
So it's d cubed 1.
This will be d squared
Plus 1. Y.
All right. So then this will be, if my y, now let's put in there our solution. Where'd it go? Thank God we don't have to FOIL, don't get all freaked out. I apply that to this, and I apply that to this. So that would be d squared c1 sine x plus, yeah, sure. Plus c2 cosine x plus c1 sine x plus c2 cosine x. Now, we know that it's linear. I can do this. So then I get d squared c1 sine x. I might as well just put this one. We know that that's 0 because sine works. Plus, and then I can get my cosine shit together. We know that's 0 because cosine works. So this idea of superposition of things that solve homogeneous, homogeneous differential equations, it works, and it's related to the fact that differential operators are linear. Those go hand in hand. This is awesome. If I find a couple answers, I slap them together, and that's a more general answer now. Okay. And we've actually talked about that idea a little bit before. How are we doing? What's up, you guys? I love it. You always look so concerned, but then there's no questions. You're like, I'm concerned that I have no idea how to formulate a question. I don't know what you want. Shit. Some of this is old stuff. We've talked about it before, but we're going to get more into just actually applying this shit finally. Let's see, what else I want to say here. Do I really want to say that? Yeah. I already said that. Cool. I like it. So let me do my... Yeah, that's old. Okay. Let me do my little example here. I like it. So, here's this main idea we're going to be applying when we're solving these differential equations. Does it make sense? Would you expect that it would be easier to work with it equal to 0 than it would be to work with it equal to some arbitrary function of x? I would say, yeah, that should be easier. In fact, if I do this, it'll screw it to hell. We're not really prepared for this yet. So if I just do this one thing, now you definitely cannot just on inspection figure out what's going to work there. But let me make it a little easier. Let me take it one step back to illustrate the next point. Okay, that's a little too much for us. And I don't know if you're really thinking about it right now. Obviously, y can't be x. Right, well, does y equal x work?
No.
Yeah, good, I like it, yes. So I probably wanted to say this. There we go, it's better. So let me look at this. Does y equal x work? Yes, why? Because y double prime of x, well, you know, if y is x, what's the second derivative of x? 0, I love it. So that does work. So let's work with this. That's awesome, I didn't even think about it. So y equals x is a solution. And now, stay with me, this is interesting. We already solved this. This is called the associated homogeneous differential equation. So the associated is this guy. So we've already solved that. Any part of this solution makes the differential equation equal 0. Now really think about that. So I already know the answer. One answer to this is y equals x. Now I can make a more general solution by realizing if I just include these, it's still going to work. Because what do each of these make this come out to be? 0. And then this guy makes it come out to be x. So the actual answer is going to be c1 sine x plus c2 cosine x. And to be honest, well, let's just say this for you, plus x. So this is interesting. This is how you have to get a complete solution. You have to first figure out the answers to the associated homogeneous differential equation. Those are the things that make it 0. And then if I add in everything that makes this work, altogether it still works. Because do these screw with this? No, because these make it 0. Plus whatever the hell this makes it. And this makes it this thing. So together they still make it work. So the idea of a general solution includes particular solutions plus these guys, the ones that come from the associated homogeneous differential equation. Yes?
So on the homogeneous, that function of y starts at 0, but when you have a non-homogeneous, it starts at whatever equals, so it starts at x. Right?
Well, I mean, it's
how they do it is, so a homogeneous starts at the origin, and then with that, start at x in a way. You see what I'm saying?
I see what you're saying.
Whatever number is.
But see, x is whatever it wants to be. That's the problem. So you can't quite break it down to what you're thinking. I know what you're thinking. It doesn't quite match up with that perfectly. I'm not sure if it would work out if I just made that a constant either. So don't think that way.
Okay.
Yeah. But if I'm given something that equals g of x, that equals some function of x, I have to first do this. We're always going to first rewrite this equal to 0, solve that, and that's going to be a part of my final answer. And please, dear God, let that make sense. These things are not going to screw with what this wants to make this do, because these things are going to make it 0. You're just going to get out the way.
Will that be the bulk of work?
Bless you.
The associate homogeneous?
So you can imagine that the more difficult this becomes, and the more difficult this becomes, the more difficult this becomes.
Okay.
Right? This one will always have really nice ways to do it. This one could sometimes have much more complicated, sometimes easy as shit. Here, this is just by observation. But I mean, if I start throwing higher level or start throwing some other coefficients out there, make this a more disgusting function, then it becomes a little bit harder process. I like it, maybe. Bless you. Oh yeah, that's right. That's what I was thinking. Here, watch. Let's try one more of these before we move on. What about y prime plus y equals 4? What's the associated homogeneous differential equation?
Y prime plus y equals 0.
That's crazy. All right. That question's awesome. You want more of those questions. But unfortunately, there's only one of those per problem. Now this you should be able to figure out on inspection. I want to let you guys think about that. Don't say anything out loud. It's not a second derivative, so it's not going to be a trigonometric function. Because they don't match up derivatives next to each other. They match up two derivatives apart, they match up again. So that's not going to work here. So what type of function do you think this is going to have to be?
Is it E?
Yeah, it's got to be E. The only function we know that really works this way that is directly related to its own derivative is E. I like it. And in fact, if this would have been minus, this could have been an E also, right? So let's see, if, what do you want to say? What's a good, well,
E to the negative.
yeah, it's got to be E to the negative x. I love it. And in fact, to be more general, would 2e to the negative x work?
No.
Why not?
Yeah.
Yes. Of course it would work, right? C e to the negative x, what's y prime? If I put c to the negative x, what's y prime? Negative c e to the negative x, right?
I thought you meant 2 to the power of.
No,
Yeah.
sorry. I mean, as a coefficient. So you see this a lot with exponential solutions. You'll see that constant getting thrown out as a coefficient. You'll see that. And this is really why. All right, so these, so what's, that so far is my only, like, general solution. I don't have a superposition thing to do yet. But what do I get for this? This one I can do as easily as this one, really, even easier. What does y have to be so that y prime plus y is 4? Yeah, it's got to be 4. I like it. So y equals 4. So now if I put those two together, I get y equals c e to the negative x plus 4. I like it. So if it was b, it would be plus b. I like it. So this idea of first making it 0 and figuring out the answers that would just kind of be there in the background. They make the whole thing 0. So they can be included because they're not going to screw with the answers that make it actually come out to be this. So I got to figure out what they are first. What are the things that I can include that aren't going to screw with what this wants to make it? So that's when you make it the associated homogeneous. You get those. Then, of course, the next level of this is what methods are there, Jeff, for when this gets really disgusting and I can't do this by-site business, right? Because this by-site business is not going to hold up for very long at all. All right, well, that would be the next step. We're not quite there yet. Let me think. There's some things in the back of my brain I forgot about. Oh, this is just a little bit important. There is an existence of a unique solution theorem for this too, which is great. And it's really nice because it's a little bit easier than the first one. And I want to ask you, have you ever run across this phrase, necessary and, I wonder if you guys have ever, sufficient? So necessary is if you wanted to plant a garden, give me one thing that is necessary in order to do that.
Soil.
Yeah.
Or plant.
You need seeds. All right. So each of those separately are necessary. Is any of them alone sufficient? If I have seeds, I can now make a garden, except I have no land. Oh. So I mean, it's necessary. There's several things that could be necessary. Sufficient means you have enough to get a garden going, right? So if I had everything I needed for a garden, and I had a TV, and I had some shoes, and are those necessary? But that collection is sufficient. They might be more than I need, but it's sufficient. So necessary and sufficient would be the most efficient way of doing it. Everything's necessary, and this is what you need to get it going. That would be. I don't need that TV right now to do the garden thing. I got my phone. I can watch the How to Garden on YouTube on my phone, right? Of course, 1980s, man, wouldn't have a clue what the hell that was all about. Let me think. Oh yeah, that's right. So this theorem is sufficient, but it's got parts that aren't always necessary. But it's kind of like, this is why it's a little bit better, because it works for everything. You don't have to get too detailed. So that first, I'm not going to keep writing this thing over, but let me just put the first thing down so you remember. Blah, blah, plus blah, blah, blah. So if all of these coefficients are continuous on some interval, all continuous on I, an of x does not equal 0 for any x on I. Let me put for all x. That little thing means for all. Let me see, what else am I forgetting? And if x naught is an element of I, x naught would be part of the initial value problem. Remember that? Y of x naught is y naught blah, 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 blah. So if x naught is in this interval, all of these are continuous on the interval. The first guy is not 0 for any x on that interval. Then you definitely have a unique solution that exists. Then there exists, have you ever seen that? Not yet. A unique solution y of x on I. Bam. I like it. So it's a nice one. You just need continuity of the coefficient functions, and you need the first one to not be 0 for any x. Then you're guaranteed a unique solution exists that kicks ass.
Is that 0 to the 10th x, or is that like a symbol? A sub n x.
Oh, yeah, this means for all x.
Oh, for all.
Yeah, this little symbol means for all. I like it. Yeah, my proofwriting class, you really got to know these really well. You start to appreciate them. You start to, that's a lot of letters if you have to write it 80 times in homework. So thank God for the little symbol, right? Okay, what else do I want to do tonight? I want to let us out really early tonight. Is that okay? Sure. No, I've had somebody get upset. I pay for your time. All right. You'll get me fired. Two things I want to talk about. Let me just put them up here. We're not going to fully talk about them. And again, I know I keep saying this, and I'm going to continue to say this, so just deal with it. If you've taken linear, you're going to have a lot of work already done to understand a lot of this. Right? Now, if you're going to take linear after this class, your teacher for linear will be saying the same shit about this class. If you've already taken different Q, then you can understand all this shit. So it'll be turned around. If you don't ever take linear, then you can't ever have experience. There's the idea of linear independence. So functions can be linearly independent or they can be linearly dependent. Starts off as a very simple idea, but once you start getting higher order DEs, you eventually have to do something called the Wronskian. Oh yeah. That should sound familiar to a few people in here, maybe. And this involves finding the determinant of a matrix. Now, before some of you guys say, well, I know how to do that on my calculator. I know the matrix button. Ha ha ha, Jeff. Well, this is going to be a matrix of functions inside. A ha 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 student, right? Too damn bad. You're still going to have to be able to figure out this determinant. So it's kind of nifty. It's functions and the derivatives. It's the square matrix. Depends on the order of the differential equation we're working with. And if I determine the solution, that determinant of the Wronskian that I create, it tells me if they're linearly independent or not. Right. And the idea of linear independence just means if I put three solutions down, if I said y equals c1 e to the 4x plus c2 e to the negative 2x plus c3 over e to the negative 4x, Now, this is a very silly example, but do I need all that shit? No, I don't, because this last dude is the first dude. I just suck the constants together and make C4 if I need to. Do you guys understand what I'm saying? So it's of course going to be a little bit more difficult to determine sometimes. This is a little bit in your face, but I have to put this together to really see if things are linearly independent, especially when they start having lots of parts to them. Or there's trig identities I don't realize are happening. What's really nice is if you do some derivatives on trig, they start to line up better even if you forgot the freaking identities. It's kind of nice. They kind of work themselves out very often, not always. Okay, we'll see that in action eventually. I personally think that's enough. Yes?
How big of a determinant?
It depends on the order of the DE. So obviously we're not going to be doing like a ton of 10th order differential equations, yeah. You could run into those out in the wild. All right. So if I were you, I would read the shit out of section 4.1. My God. Okay. Yes.